In this lecture, we will look at a very simple yet powerful classification algorithm called the k nearest neighbors. So, let me introduce k nearest neighbor classification algorithm. It is what is called a non-parametric algorithm for classification. So, let me explain what this non-parametric means. Remember, when we looked at logistics regression, for example, we said let us say there is data like this, and we are going to use the trained data to develop a hyperplane of this form beta naught plus beta 1 1 x 1 plus beta 1 2 x 2 in the 2D case. And any time a new data point comes, what we do is we use the parameters that have been estimated from the trained data to make predictions about test data. So, remember we had this e power this term divided by 1 plus e power this term right here. So, this function is actually a function of beta naught, beta 1 1 and beta 1 2. So, these are all parameters that have already been derived out of this data, and any time a new test data comes in, it is sent through this function and then you make a prediction. So, this is a parametric method because parameters have been derived from the data. K nearest neighbor is a different idea where I do not get parameters like this out of the data. I am going to use the data itself to make classification. So, that is an interesting different idea that one uses in k nearest neighbors. I just want to make sure that we get the terminology right. We will later see that the k nearest neighbor, there is one parameter that we use for classifying, which is the number of neighbors that I am going to look at. So, I do not want you to wonder, since we are using anyway a parameter in this k nearest neighbor, why am I calling it non-parametric. So, the distinction here is subtle, but I want you to remember this. The number of neighbors that we use in the k nearest neighbor algorithm that you will see later is actually a tuning parameter for the algorithm. That is not a parameter that I have derived from the data, whereas in logistics regression these are parameters I can derive only from the data. I cannot say what these values will be a priori, whereas I could say I will use a k nearest neighbor with 2 neighbors, 3 neighbors and so on. So, that is a tuning parameter. So, I want you to remember the distinction between a tuning parameter and parameters that are derived from the data, and the fact that k nearest neighbor is a non-parametric method speaks to the fact that we are not deriving any parameters from the data itself. However, we are free to use tuning parameters for k nearest neighbor. So, that is an important thing to remember. It is also called a lazy learning algorithm, where all the computation is deferred until classification. So, what we mean by this is the following: if I give trained data, for example for logistics regression, I have to do this work to get these parameters before I can do any classification for a test data point, right. So, without these parameters I can never classify test data points. However, in k nearest neighbor you just give me data and a test data point, I will classify. So, we will see how that is done, but no work needs to be done before I am able to classify a test data point. So, that is another important difference between k nearest neighbor and logistic regression, for example. It is also called as an instant based learning, where the function is approximated locally. So, we will come back to this notion of local as I describe this algorithm. Now, we might ask when do we use this. As I started this lecture, I mentioned it is the simplest of classification algorithms, very easy to implement, and you will see when I explain the algorithm how simple it is. There is no explicit training phase and so on, and there is no generalization for the training data and all that. It is just that I give the data and then I just wait till you give me a new data point to say what class it should belong to. Of course, based on the algorithm itself, I can also predict for the trained data points itself what class they should belong to, and then maybe compare it with the label that the data point has and so on. Nonetheless, I am not going to explicitly get some parameters out. And when does one use this algorithm? This is a simple algorithm when there are complicated nonlinear decision boundaries. This algorithm actually works surprisingly well, and when you have large amount of data and the train phase can be bogged down by large amount of data in terms of an optimization algorithm and so on, then you can use this. However, a caveat is you will see as we describe this algorithm, when you have more and more data, the classification of nearest neighbor itself will become complicated. So, there are ways to address this, but when we say when the amount of data is large, all that we are saying is since there is no explicit training phase, there is no optimization with a large number of data points to be able to identify parameters that are used later in classification. So, in other words, in other algorithms you will do all the effort a priori, and once you have the parameters, then classification becomes on the test data point becomes easier. However, since kNN is a lazy algorithm, all the calculations are deferred till you actually have to do something. At that point, there might be lot more calculations if the data is large. So, the input features for nearest neighbors could be both quantitative and qualitative, and output are typically categorical values, which are what type of class does this data belong to. Now, it is not necessary that we use k-nearest neighbor only for classification, though that is where it is used the most. You could also use it with very simple extensions or simple definitions for function approximation problems also, and you will see as I describe this algorithm how it could be adapted for function approximation problems quite easily. Nonetheless, as far as this lecture is concerned, we are going to say the outputs are categorical values, which basically says different classes and what class does this data point belong to. In one word, if you were to explain k nearest neighbor algorithm, you would simply say k nearest neighbor explains a categorical value using the majority votes of nearest neighbors. So, what basically we are saying is if there is a particular data point and I want to find out which class this data point belongs to, all I need to do is look at all the neighboring data points and then find which class they belong to, and then take a majority vote, and that is what is the class that is assigned to this data point. So, it is something like if you want to know a person you know his neighbors, something like that is what is used in k nearest neighbors. Now, remember at the beginning of this portion of data science algorithms, I talked about the assumptions that are made by different algorithms. Here for example, because this is a non-parametric algorithm, we really do not make any assumptions about the underlying data distribution. We are just going to look at the nearest neighbors and then come up with an answer. So, we are not going to assume probability distribution or any other linear separability assumptions and so on. As I mentioned before, this k, the number of neighbors we are going to look at, is a tuning parameter, and this is something that you select, right. So, you use a tuning parameter, run your algorithm and you get good results, then keep that parameter. If not, you kind of play around with it and then find the best k for your data. The key thing is that because we keep talking about neighbors, and from a data science viewpoint, whenever we talk about neighbors, we have to talk about a distance between a data point and its neighbor. We really need a distance metric for this algorithm to work, and this distance metric would basically say what is the proximity between any two data points. The distance metric could be Euclidean distance, Mahalanobis distance, Hamming distance and so on. So, there are several distance metrics that you could use to basically use k nearest neighbor. So, in terms of the algorithm itself, it is performed using the following 4 steps. Nothing is done till the algorithm gets a data point to be classified. Once you get a data point to be classified, let us say I have n data points in my database and each has a class label. So, for example, x1 belongs to class 1, x2 belongs to class 1, x3 belongs to class 2, and so on, xn belongs to let us say class 1. So, this is a binary situation, binary classification problem. This need not be a binary classification problem. For example, x2 could belong to class 2 and so on. So, there may be many classes. So, multi-class problems are also very easy to solve using kNN algorithm. So, let us anyway stick to binary problem. Then what you are going to do is, let us say I have a new test point which I call it x new, and I want to find out how I classify this. So, the very first step, which is what we talk about here, is we find a distance between this new test point and each of the labeled data points in the data set. So, for example, there could be a distance d1 between x new and x1, d2 between x new and x2, d3 and so on, and dn. So, once you calculate this distance, then what you do is you have n distances, and this is the reason why we said you need a distance metric right in the last slide for kNN to work. Once we have this distance, then what we do is basically we look at all of these distances and then say I order the distances from the smallest to the largest. So, let us say if dn is the smallest distance, so dn may be d5, d3, d10, whatever it is. So, I order them, this is the smallest to the largest. You can also think of this as closest to the farthest, right, because the distances are all from x new. So, if the distance is 0, then the point is x new itself. So, any small distance is the closest to x new, and as you go down it is farther and farther. Now, the next step is very simple. If let us say you are looking at k nearest neighbors with k equal to 3, then what you are going to do is you are going to find the first 3 distances in this, and this distance is from xn, this distance is from x5, and this distance is from x3. So, once we order this according to distance and go from the smallest to largest, once we sort it in this fashion, then we also know what the corresponding data points are. So, this is the data point xn. So, this is the distance between xn and x new, distance between x5 and this. So, now I have these 3 data points that I picked out from the data set. Now, if I want to classify this, all that I do is the following. I find out what class these data points belong to. So, if all of them belong to class 1, then I say x new is class 1. If all of them belong to class 2, I say x new is class 2. If 2 of them belong to class 1 and the third one belongs to class 2, I do a majority vote and still say it is class 1. If 2 of them belong to class 2 and 1 belongs to class 1, I say it is class 2. That is it, that is all the algorithm is. So, which says to find the class label that the majority of these k labeled data points have and assign it to the test data point. Very simple, right. Now, I also said this algorithm with minor modifications can be used for function approximation. So, for example, if you so choose to, you could take this and then let us say if you want to predict what an output will be for a new point, you could find the output value for these 3 points and take an average, for example, very trivial, and then say that is the output corresponding to this. So, that becomes adaptation of this for function approximation problems and so on. Nonetheless, for classification this is the basic idea. Now, if you said okay, k is equal to 5, then what you do is you go down to 5 numbers and then do the majority voting. So, that is all we do. So, let us look at this very simple idea here. let us say this is actually the training data itself, and then I want to look at k equal to 3 and then see what labels will be for the training data itself. The blue are actually labeled. So, this is supervised, right. So, the blue are all belonging to class 1 and the red is all belonging to class 2, and then let us say for example, I want to figure out this point here, blue point. Though I know the label is blue, what class would k nearest neighbor algorithm say this point belongs to? Say if I want to take k equal to 3, then basically I have to find 3 nearest points, which are these 3. So, this is what is represented, and since the majority is blue, this will be blue. So, basically if you think about it, this point would be classified correctly and so on. Now, even in the training set, for example, if you take this red point, I know the label is red. However, if I were to run k nearest neighbor with 3 data points, when you find the 3 closest point, they all belong to blue. So, this would be misclassified as blue even in the training data set. So, you notice one general principle is there is a possibility of data points getting misclassified only in kind of this region where there is a mix of both of these data points. However, as you go farther away, the chance of misclassification keeps coming down. So, again in some sense you see a parallel saying, okay, if I were to draw a line here and then say this is all red class, this is all blue class, then points around this line is where the problem is, right. As they go farther away, the problems are less. Nonetheless, notice how we have never defined a boundary line or a curve here at all, right. The data points themselves tell you how this boundary is drawn. So, in that sense, it's while it is simple, it is also in some sense sophisticated, because we never have to guess a boundary. The data points themselves define boundary in some sense. So, I can actually effectively use this algorithm for complicated nonlinear boundaries, which you would have to guess a priori if you were using a parametric approach. So, that is the key idea here. A similar illustration for k equal to 5. Now, if I want to let us say check this data point from the training set itself, then I look at its 5 neighbors closest 1, 2, 3, 4, 5, all of them are red. So, this is classified as red and so on. So, this is the basic idea. Now, you do not have to do anything till you get a data point. So, you could verify how well the algorithm will do on the training set itself. However, if you give me a new test data here, so which is what is shown by this data point, then if you want to do a classification, there is no label for this. Remember, the other red and blue data points already have a label from prior knowledge. This does not have a label. So, I want to find out a label for it. So, if I were to use k equal to 3, then for this data point I will find the 3 closest neighbors, they happen to be these 3 data points. Then I will notice that 2 out of these are red. So, this point will get a label class 2. If on the other hand the test data point is here and you were using k equal to 5, then you will look at the 5 closest neighbors to this point, and then you see that 2 of them are class 2 and 3 are class 1. So, majority voting, this will be put into class 1. So, you will get a label of class 1 for this data point. So, this is the basic idea of k nearest neighbor. So, very simple. However, these are some of these the things to consider before applying kNN. So, one has to choose the number of neighbors that one is going to use, the value of k, whether it is 3, 5, 7, 9, whatever that is, and the results can quite significantly depend on the parameter that you choose, particularly when you have noise in the data, and that has to be taken into account. The other thing to keep in mind when using kNN is that when you do a distance between 2 data points x1 and x2, let us say, and let us say there are n components in these, the distance metric will take all of these components into picture. So, since we are comparing distance, then that basically means every attribute for this data point and this data point we are comparing distances. The problem with this is that if for example, there are a whole lot of attributes which actually are not at all important from a classification viewpoint, then what happens is, though they are not important from a classification viewpoint, they contribute in the distance measure. So, there is a possibility of this features actually kind of spoiling the results in k nearest neighbor. So, it is important to pick features which are of relevance in some sense. So, the distance metric actually uses only features which will give it the discriminating capacity. So, that is one thing to keep in mind. The other the problem is these are handleable, these are rather easily handled, but these are things to keep in mind when you look at these kinds of algorithms, and also particularly this being the first course on data science, I am assuming for most of you, these are kinds of things that you might not have thought about before. So, it is worthwhile to kind of think about this, do some mental experiments to see why these kinds of things might be important and so on. Now, the other aspect is scaling. So, for example, if there are two attributes, let us say in data temperature and concentration, and temperatures are in values of 100, concentrations are in values of 0.1, 0.2 and so on. When you take a distance measure, these numbers will dominate over this. So, it is always a good idea to scale your data in some format before doing this distance. Otherwise, while this might be an important variable from a classification viewpoint, it will never show up because these numbers are bigger and they will simply dominate the small number. So, feature selection and scaling are things to keep in mind. And the last thing is curse of dimensionality. So, I told you that while this is a very nice algorithm to apply, because there is not much computation that is done at the beginning itself. However, if you notice, if I get a test data point and I have to find, let us say, the 5 closest neighbors, there is no way in which I can do this, it looks like, unless I calculate all the distances. So, that can become a serious problem if the number of data points in my database is very large. Let us say I have 10,000 data points, and let us assume that I have an algorithm, k nearest neighbor algorithm with k equal to 5. So, really what I am looking for is finding 5 closest data points from this database to this data point. However, it looks like I have to calculate all the 10,000 distances and then sort them and then pick the top 5. So, in other words, to get this top 5 I have to do so much work, right. So, there must be smarter ways of doing it, but nonetheless one has to remember that with number of data points and number of features, one has to think how to apply this algorithm carefully. So, the best choice of k depends on the data, and one general rule of thumb is if you use large values for k, then clearly you can see you are taking lot more neighbors. So, you are getting lot more information. So, the effect of noise on classification can become less. However, if you take a large number of neighbors, then your decision boundaries are likely to become less crisp and more diffuse, right. So, because if let us say there are 2 classes like this, then for this data point if you take a large number of neighbors, then you might pick many neighbors from the other class also. So, that can make the boundaries less crisp and more diffuse. On the flip side, if you use smaller values of k, then your algorithm is likely to be affected by noise and outliers. However, your decision boundaries as a rule of thumb are likely to become crisper. So, these are some things to keep in mind, and as I mentioned before, it is important to remove irrelevant features, and scaling is also an important idea. So, if you choose your features carefully, then you would get better classification with kNN. So, with this we come to an end of this lecture on k nearest neighbors, and following this lecture there will be a case study which will use k nearest neighbor that will be taught by one of the teaching assistants, and after that I will teach a lecture on k means clustering. Thank you, and I look forward to seeing you again in a future lecture. Thanks.